Thank you for all coming. We're pretty proud of this presentation and the fact that we're all cooperating together, so it'll be interesting. The title slide there says Stalling Transport Aircraft, and that is indeed what we're going to talk about. The subtitle is what I was just referring to. It is a joint Boeing and Airbus presentation, and in fact, as far as we're aware, this might be the first ever joint Airbus Boeing presentation. And depending on how our corporate entities do, if we do really well tonight, we might want to do one of these again. If not, you'll never see us together. We've just handled the introductions. You'll get to hear from all of us in turn. A little bit of a fire drill as we go through the exchange of speakers here. For the most part, it'll flow pretty smoothly. We will be taking questions at the end up here in the panel position. You've met all of us, at least through introduction, and as we hand off, we'll at least use first names to let you know who's speaking next. In terms of an agenda or the outline for a presentation tonight, we're going to start off with defining a stall. What is a stall? How do you define a stall? Talk a little bit about regulations, requirements for a stall. We'll then move into talking about how engineering prepares for conducting stall campaigns and for the most part for any flight test campaign, but stall campaigns in particular, including the build-up and prep work, and also we'll talk about instrumentation. We'll then hear about pilot preparations and the kind of briefings that pilots do getting ready to conduct a flight test campaign. Then more specifically talking about the actual conduct of a stall flight test campaign. Towards the end, we'll briefly foray into what the future of stall testing might be, mostly in the form of questions that I will address. And then obviously we'll summarize and conclude at the end. And then following the formal presentation, as I mentioned, we'll be taking any questions and answers. We'll be taking any questions, whether we answer, it depends on what the questions are. Without further ado, I'm going to pass the ball to Stephane Vaux, who will start off the real heart of the material.
Thank you, Paul. Good evening, ladies and gentlemen. Before starting, I would like to apologize for my poor English. I'm probably the only French here in this assistance, and I'm afraid that my French is as bad. My English is as bad, but my French too. But my English is as bad as the French team plays rugby. I'm sure you mean what I understand. I'm sure you understand what I mean. Okay, so let's talk about let's try to define what is a stall. First, when we develop a brand new aircraft, very early in the flight test campaign, we have to do stall testing. And there are many different proposals or many results awaited from these tests to catch with the following targets. First, we have to very rapidly open the flight envelope of the aircraft. And we have to assess the handling qualities of the aircraft towards the stall. The stall test is also very important to optimize the aerodynamic configurations in order to get a good compromise between low speed and high speed, for example. So if the designers have worked perfectly, we do not have to spend a lot of time to the aerodynamic configuration optimization, but it can happen sometimes that we have to spend some time to tune perfectly the aerodynamic configurations. Another thing which is really important is to draw or to identify perfectly the aerodynamic of the aircraft by tracing the CL alpha curves of each aerodynamic configuration. I will detail that in the next slide. We have to determine also the stall speeds, which are called VS1G or lately VSR in the regulation, on which a lot of performances are based, such as the V2, the final takeoff speed, the VREF, approach speed, minimum approach speed. We have also, well, the stall is also, stall testing is also the opportunity to check what are the stall margins regarding the horizontal tail of the aircraft. So we take a particular attention, we keep particular attention to that point. And of course, during the stall test, and particularly during the recovery, that will be deeply explained later on, we have to keep attention on the loads, regarding the loads on the horizontal tail. At the end of the development test campaign, stall test campaign, of course, we have to do some certification tests, certification stall, in order to properly trace in the certification cards the characteristics of the aircraft, and particularly this CL alpha curves. So, what is the definition of a stall? The stall is defined as the point when maximum aerodynamic lift is achieved, which means that further increase of angle of attack beyond the point of the stall will cause automatically a reduction of lift. So here you have an example of the lift, the CL alpha curves we can draw following based on the data reduction after the test. So here on the y-axis you have the lift counts, and on the x-axis you have the angle of attack. What is interesting is that you have to remember that if I take this configuration, aerodynamic configuration, clean, which corresponds to the cruise configuration, so where the leading edges and trailing edges of the wing are retracted, this curve, those curves, take into account the whole aircraft lift. But of course, the majority of this lift is brought by the wings, but not only. There is a lift which is in fact not brought but decreased due to the horizontal tail, and in a very less extent, or much less extent, the fuselage also is contributing to the total aircraft lift. So what we can see on those curves is that if you compare the conf clean CL max, so yes, just to point out, here you have you can see what we call the CL max and the stall angle, or the angle at which we reach the CL max. And you can see particularly on that curve that beyond that point there is a sudden reduction of lift. So what we can, if we try to compare those curves, we can see that what is the main benefit brought by extension of the slats of the leading edge devices on the wing, it's that it's a very big increase in the stall angle. Also an increase on the lift count, but mainly a very big increase of stall angle. Then the other configurations, for the other configurations, the slats are already extended, they are more extended. But what we see is that here the flaps are extended. As the more you extend the flaps, and the higher the CL will be. Okay, that's something which is systematic on all transport aircraft fitted with slats and flaps. Slats are increasing the stall angle, flaps are increasing the CL max. Okay. What is remarkable is that when we are doing stall tests, when we reach the CL max, depending on the aircraft, but also depending on the aerodynamic configuration, you can have a sudden loss of lift, which will be translated in the real aircraft in real time by a sudden loss of vertical load factor. And this is what we call the G brake. And so the stall of the aircraft will be detected by this sudden G brake. Of course, when you have a curve which is very flat, as this one in Kung Fu here, you cannot see a real sudden lift decrease. So you will not detect any G brake, but most probably you will see that the angle of attack is increasing, and the sink rate of the aircraft will be also increasing. But there's no particular G brake. Okay. So based on the CLmax determination, as it was here, we are able, thanks to the lift equation, don't worry, I will not enter into detail the lift equation, but we are able to compute the VS1G or the VSR based on that equation. And this VSR or VS1G is defined as the minimum speed at which the aircraft can generate enough lift to maintain a 1G condition. It's very important, this speed, because, as I said before, a lot of performance speeds are computed based on this VS1G or VSR. So what is interesting is that on the CL curve, CL alpha curves are shown to you, there are many different effects that have a direct impact on the CLmax, and of course also on the VS1G or VSR. And those impacts or those effects have to be identified during a flight test campaign, and particularly during development flight test campaign, well before the certification. So we'll try to review all the main, the significant effects which affect the CLmax. The first one is the CG effect, the center of gravity effect. As I said before, the total lift of the aircraft is composed mainly by the wing lift, the lift produced by the wing, a little bit by the fuselage, and the horizontal tail. But the horizontal tail produces a downward lift, contrary to the wing. So, depending on the horizontal tail position, the trim, the pitch trim position, you will have an effect on the CLmax. Okay? And this what is illustrated on those curves. You see for a given configuration, for example here, so here in the y-axis you have the CLmax, okay? For the clean configuration, for example. You see that at aft CG, 44% of CG, you have more lift than at forward CG, 28% of CG. Okay? And it's the same for all configurations. Which means if you transfer that into speed, VS1G, VSR, you will get lower VS1G at aft CG than at forward CG. And that's the reason why all performance speeds are computed at forward CG. Of course. The most critical one. So this is the CG effect. Another effect, which is not immediate when you think about it, it's the thrust effect. On almost all transport aircraft, at least the Boeing and the Airbus aircraft, the wings are installed under the wings. And it is not because they are under the wings that they don't have an effect. In fact, the effect of the thrust is mainly due to the vertical component of the force induced by the thrust. Okay? And what you can see is that the higher the thrust is, here you have 100% of thrust, the more you have lift. Okay? And this applies, of course, for all aerodynamic configurations. Okay? Well, just if you look at the scale, the amplitude is not a lot. You go for clean configuration, for example, you go from 120 lift counts to 135. But it has an effect, which has to be identified. So in terms of flight tests, we are not doing stalls with full thrust, because it could be dangerous, and I'm not sure we could even reach the result, the awaited result. So we generally do stalls, powered stalls. We call them powered stalls. Let's say at something like between 20 and 40% of thrust. But generally, it's a linear function, so we can extrapolate to 100% of thrust. There are some, so this applies for turbojet aircraft. But for propeller aircraft, you have an additional effect, which is called the CT effect, which is the result of the blowing. The propellers are blowing the wing, and by this way, the wings are regaining lift. This is, for example, for the Airbus military aircraft, the A400M, which is fitted with huge propellers. This effect, the CT effect, is huge, really huge. Another effect, which is really, really important, it's the Mach number effect. What you can see on this curve is when you increase the Mach number, the CL max is decreasing. And this is true whatever the configuration. Of course, it's more marked, let's say, more abrupt in the clean configuration, in the cruise configuration, but it exists also on the high lift configurations. The reason of that is when you increase the Mach, you have some local shock waves which are created and which degrade and destroy the lift. Okay? But it's really local shock waves. And that's the reason why the Mach number has a huge effect on the CL max. This is true at low altitude. For example, those curves are issued from tests performed at around 10,000 feet. But at high altitude, it's even worse. Okay? But there is another phenomenon at high altitude which occurs, which is what we call the buffeting. In fact, at high Mach and at high altitude, you are not able to reach the CL max, let's say the theoretical CL max of the aircraft, and so you are not able to compute the VS1G or VSR, because before reaching that CL max, you encounter a very strong buffeting, and which can be very, very deterrent buffeting. Therefore, if we look into the regulation, there is a clear definition of what must be the CL max at high Mach and high altitude. For each flyable Mach number, we have to demonstrate that we have at least 1.3 G's maneuverability. So you have to be able to perform a turn pulling up to 1.3 G, okay, before you are reaching what we call the buffet onset. And this buffet onset is clearly identified and defined in the regulation. We put an accelerometer on the pilot seat station, and we measure the high frequency accelerations, and we define the buffet onset when we reach plus minus 0.1 G vertical acceleration. So if you have 1.3 G maneuverability when reaching the buffet onset, you can say I've reached the CL max for that Mach number. Okay? Which means that, well, the reason there is an effect which reduces the CL max at high Mach number is the same at low speed. It's the local shock waves. Of course, you have much more shock waves along the wing at high Mach than at low Mach. In addition, the buffeting defined in the stall occurs at a lower angle of attack for the high Mach numbers. Okay, so we will see that later on, but this induces some reduced margins during a stall recovery at high Mach, and you will see what are the precautions to be taken to recover from a stall at high Mach. So if I try to illustrate that in a curve, here's the. So here it's we call that no more CL max, but CL of buffet, of buffeting, or the CL of buffet onset, and we can see that when you increase the Mach number, so I don't know if you can read the figures, going from 0.82 to 0.89, you see clearly that the angle of attack, or the CL, sorry, the CL of buffeting is decreasing as long as you increase the Mach number. Here, it's the same phenomenon, but when we look to the alpha, to the angle of attack of the buffeting. So you see that the angle of attack at which the buffeting, the buffet onset, appears is reducing drastically when the Mach increases. Except at very, very high Mach numbers where we observe the contrary. Don't ask me why. I'm not an aerodynamicist, and I don't know. But just for your information, 0.9 of Mach number, 0.95, it's well above the maximum operational Mach number, either for Boeing aircraft or Airbus aircraft. But we try to identify that in test as well. Okay, there is another phenomenon which can be very surprising when you are flight testing stalls. It's what we call the pitch-up. Oh, by the way, I've forgotten to say that I'm talking about CL max determination when we are performing stall tests and so on. Sometimes you cannot reach CL max for other reasons than the reasons I've mentioned before. For example, if you have, before reaching a CL max, if you reach full stick, full aft stick, and you cannot, and your angle of attack is not increasing anymore, in fact, you will declare the CL max when you reach full stick. Another phenomenon, which is less convenient, let's say, you can have some wing drops, roll off, or very sudden pitch up. So if you have no way to improve that aerodynamic phenomenon, then you will be obliged by regulation to declare the CL max at the appearance of that phenomenon. But generally, we are trying to improve the aerodynamic configurations when such a phenomenon occurs. So coming back to the pitch up, a pitch up can be observed during stall mainly on aircraft fitted with swept wings, which is generally the case for Boeing and Airbus transport aircraft. It is due to the sudden loss of lift on the outer part of the wing, which creates a nose-up pitching moment. So I've tried to illustrate that. Here is an aircraft, and here is more or less the CG location. So the wings are producing lift all along the wing, and at a given angle of attack, in combination, either in combination with a Mach number or only at very low Mach number, only depending on the angle of attack, you can have a sudden loss of lift on the outer part of the wings. And you see that the outer part of the wings is behind the CG. So this will result in another pitching moment. Again, this sudden loss of lift can be only due to the high angle of attack or in combination with a high Mach number or local shock waves which appear in this area. Okay. So this phenomenon, what we call the pitch up, can occur at low altitude or high altitude. And at high altitude, it can occur at very low Mach number, very low angle of attack, sorry, but for high Mach numbers. So this is a phenomenon which we have to take into account, and particularly during flight testing, we have to be prepared to face such a phenomenon, which can be more or less violent depending on the aircraft. And I will let Paul continue.
Right, the next effect we're going to talk about is the ground effect. Lift varies as the airplane gets very, very close to the ground. This is typically, for most of the airplanes we're talking about between Airbus and Boeing, we're talking about within the final 200 feet of altitude near the ground. It causes a cushion effect, basically, and I'll use the chart to talk about it. You see that as the airplane is in full ground effect, or at least some ground effect, there's an increase in lift in the lower angle of attack regions compared to what it was at 500 feet or above, for everything being the same configuration. However, there's often a significant reduction in maximum lift available when the airplane's in ground effect. We also perform stalls in lots of other configurations, typically considered probable failure configurations. These are abnormal high lift, abnormal flat configurations, sometimes with hydraulic failures. We do these sometimes with lateral center of gravity offsets as required by regulations. Degraded modes we'll talk about further on, but there's many, many configurations we do stalls beyond which we've shown data for here. Getting in a little bit to the regulatory environment, there are 4 regulations that are pretty much harmonized by now around the world. The first which is stall speed, 25103, then there's stall demonstration, characteristics, and warning. What these regulations do are define how to calculate that stall reference speed, formerly VS1G, now VSR. That's the 25103 paragraph. Also talks about which conditions are required to be demonstrated for stall, which in reality is pretty much every configuration you can imagine. You have to test every flap-slat combination, high lift devices, speed brake devices, all kinds of configurations. Part of 201 talks about how to identify a stall condition. This is the stall identification sub-paragraph of 201, which changed back in 1984. Basically now it's you can choose between deterrent buffet or full F column with no increase of further increase in angle of attack. Those are the 2 most prominent ones. The regulations in 203 also talk about what characteristics are acceptable for the handling of the airplane at or beyond stall. Key among these is the amount of roll-off that is acceptable should you encounter any. And 207, of course, prescribes lots of requirements for how much warning is required for a flight crew in advance of a stall. So that's a very brief overview of the regulatory environment dealing with stalls. And that kind of concludes our definition and requirements section very rapidly, stall primer, if you will. We're going to talk next a little bit about engineering preparations for a flight test campaign, not specifically just stalls, but a flight test campaign. A lot of the initial data that we gather is from wind tunnel facilities around the world. extensive, especially for obviously new airplane types, but even often for derivative airplane types, we'll go in and do at least some wind tunnel testing. That data tends to drive our early simulator models. At least at Boeing, we're dependent more and more and more on the accuracy of our simulations. It's become a very interesting topic worldwide as well. Once that simulation has been assembled from that wind tunnel data, we use it extensively for predicting what the flight characteristics of the airplane would be, stall characteristics being part of that. Obviously, we're looking for any unacceptable trends or anything that might require modifications to airplane, or these days with fly-by-wire airplanes, modifications to control laws. We also bring in our pilots early on to help us evaluate these characteristics. A lot of the things we're looking for tend to be somewhat subjective and not 100% objective, data-driven. So pilot opinion matters a lot. And we've also driven quite a bit of change into airplane designs, both physical characteristics as well as things like control laws, based on pilot feedback early on, well before an airplane has ever flown. When we start to get the entire flight test team together, we go in shortly before a flight test campaign begins and do a lot of rehearsal work in our company simulators. This is anything from familiarity with the airplane and familiarity with the characteristics to actually practicing each individual test card. Now that's not to say we practice every single test card for the entire program, but certainly a lot of the high-risk testing, there's a requirement to practice first in our simulations. Our simulations have evolved to be very useful for almost anything you can imagine within the normal flight envelope. They're very, very complex at Airbus and Boeing. The simulations that we have today are capable of almost anything. Lots of failure capabilities, very extensive, very accurate. With the combination of wind tunnel data and then the effort spent following the flight test program to update the simulator databases with flight data, they're very, very accurate. Within the normal flight envelope, including up to the point of stall, really. The stall approach tends to be very accurate to simulate. The area that's a bit problematic is post-stall. Obviously, that's a very, very highly dynamic environment. Unsteady aerodynamics are often mentioned in that region. Very difficult to predict, very difficult to model. But on the other hand, the airplanes themselves tend to be somewhat different. For instance, flying with 5 stalls in the exact same configuration, they may not all behave the same. So obviously difficulty in modeling that. There's a lot of industry work going on in this particular arena right now, which is not a subject of this paper, but perhaps another one coming up. Along with engineering and predicting characteristics, there's obviously quite a bit of work that's done with instrumentation in preparation for flight test. These days, with the advent of as much electronics as we're using, we're into the thousands or perhaps tens of thousands of channels of data available, especially on fly-by-wire aircraft that have digital buses. We still use a lot of analog instrumentation, flight test orange wire, but we make quite a bit of use of things that we can grab off of the digital buses that are already on the airplanes. The first example of an instrumentation item we'll talk about, we're going to walk through a few here, is special displays that we put on the flight deck to provide additional information to the flight crew above and beyond what a production pilot would see. This is just meant as an illustration of what that might look like. Obviously the primary flight display over to the left of this picture, and then a dedicated flight test display on the right, can provide anything from airspeed from a different source to things that aren't readily viewable by the pilot, load factor, angle of side slip. We can provide all kinds of data up to the pilot in a very useful form. So come a long ways from the old panels display with the clicking digits rolling by. This next chart is the same display, just meant to show the kinds of things that can be done these days with that kind of a display. Certainly by looking at these, you can see that there's a potential for actually overwhelming the flight crew with too much information. We have to keep engineers employed somehow, so we have to have them relying on us. Maybe we should take all this away. Another key area, especially in the area of stall, high angle of attack environment, is monitoring tail loads. This is a drawing, obviously not a photograph, but a drawing of a type of display that we install in the flight deck and also in the back of our flight test airplanes. What's meant to be indicated here is, it's kind of hard to see, but these circles here at the top are actually all lights. There are 2 green, 2 amber or yellow, and 2 red lights. And increasingly showing numbers of load factor, and that load factor is in NZ, but limit load on the horizontal tail. If you hit 100%, the last red light goes off, some portion of the horizontal tail has hit its limit load, and typically that's a return to base condition. The center display here is usually a numeric display of what percent of limit load factor was achieved in that condition, and then there's a reset button, so in between conditions we push that to reset the display. But this is a primary concern because depending on how the aircraft is flown, it's very easy to generate high tail loads in these conditions. We also, for stall, on the primary flight displays of our aircraft, have a device called the Pitch Limit Indicator, or PLI, which are these amber whiskers, eyebrows, whatever analogy you'd like to use, that provide a indication directly to the flight crew of a pitch ladder visualization of what the angle of attack for stall warning is. So this is not actually the stall angle of attack, but it's the stall warning angle of attack. Provides additional information to the crew, and you'll hear more about that during the pilot discussions. Another thing we do is early on in the aircraft program, we may not have calibrated the airspeed system well enough, so we have a trailing fin cone that we stick out the back of these. These are shown, a couple of illustrations here, these are shown in the retracted position, but typically if we're up and doing conditions where we're going to rely on this, we run them out anywhere from 90 to 180 feet behind the airplane. This provides a remote sensing of static pressure before the static ports on the airplane are calibrated. This is a close-up of what one of our cones looks like, and somewhere up in the end of the tube right here is where the actual pressure sensor is, and then it's run by a tube back into the airplane and into the instrumentation collection system. And with that, I'll go one more time back to Stephane, and we'll continue our discussion.
So still regarding the anemometry calibration, we are interested to better calibrate the total pressure measurement. So in fact, not during the very first stalls, but let's say in the middle of the flight test campaign, we remove one aircraft pitot, and we replace this pitot, generally the number 3, by a specific one, which is called a low-speed pitot, which is much bigger than the other one. You have a pitot, a normal pitot there, so you see it's a very big one, and it is manufactured by an American company, Rosemont. And the aim of this pitot is to give a very high angle of attack a precise total pressure information, and this allows to better calibrate the anemometric system of the aircraft. So this is one picture, you have another one here, and in fact we can barely see that on the picture, but here along the tube you have holes in order to catch the total pressure at very high angle of attack. But it's the same concern as for the static pressure. The idea there is to better calibrate the anemometric system of the aircraft. Another thing which is really useful when we have, unfortunately, to better set the aerodynamic configurations is to visualize the aerodynamic flow along the wing. So we install flow cones, we call them flow cones, everywhere on the wing, on the pylon, engine pylon, on the engine nacelles, and so on. We put a lot of video cameras in order to record the phenomenon. And was the voice from Claude Lelay, our former test director within the Airbus flight test organization. Okay, there is another really specific feature or device which is installed, well, up to now within Airbus we have installed that on only one aircraft, which is the military A400M aircraft. It's a tail booster for pitch recovery. In fact, this device consists in a pyrotechnic device. Well, to be simple, it's a rocket. So, and it's there in order to cover or to try to escape from what we call a deep stall. So a deep stall is a phenomenon, an aerodynamic phenomenon, which is mainly linked to a particular configuration of the tail, and particularly on the aircraft which are fitted with T-tails. And the phenomenon, the aerodynamic phenomenon, consists in the blanking of the horizontal tail by wake of the wing at high angle of attack, and the result is that you totally lose elevator and pitch trim efficiency. But when I say totally, it's really totally. You can move the stick like that, absolutely no effect. So the only way to escape from such a situation, you can try to retract if you were doing stall with the flaps extended. You can try to retract the flaps in order to get a different downwash on the horizontal tail, but generally it's not sufficient. That's the reason why, in order to protect the flight test crew, we installed such a system. So you have to imagine the work to be done on the aircraft for a single test campaign. As I said, it's a rocket, so you can imagine the structural reinforcement we are obliged to install on the test aircraft. And when you are flying, when you are doing stall on that aircraft, you know that you have a bomb just behind you. I do not feel very confident. And I cross my fingers, but up to now we didn't have to use that. But it's just to illustrate also that in flight tests there is a big word which should be written on all flight test organization is safety first. And this is, you can imagine how much time, money we spend for something that we hope we will never use. But we have to. And this is something which is really complex in all flight test organizations, is that you always have to balance the industrial efficiency and the safety of the flight testing. Sometimes you have to get power to convince your management that you have to improve the safety of the test. Okay, we take also the opportunity of the stall tests in order to look during recovery of a stall on the margin we have regarding the horizontal tail stall, and particularly the stall angle. For that purpose, we fit the horizontal tail with a specific angle of attack probe, which is there. It's this one. And we have another picture here. So you have a kind of tube there, which is fixed on the horizontal tail, and the AOA probe is there. And during the recovery, as you will recover with not full stick, but stick forward, you will reach probably the minimum margin towards the maximum angle of attack or maximum lift developed by the horizontal tail. So it's interesting to see what are the margins during those recoveries. There are specific tests which are more critical to that, where we voluntarily go towards the horizontal tail stall, which are called the pushovers, but it's another test technique than the stalling on aircraft. Artificial ice shapes. of course, you can imagine that if you fly into icing conditions, the leading edge, all leading edges, wing, horizontal tail, vertical tail, the fin, will accrete some ice, and this will have a good degradation regarding the lift, which will be developed by either the wing or the horizontal tail, or even the rudder efficiency. So we are doing a natural icing test, but of course it mainly depends on the actual conditions you can find. That's the reason why we are due for certification purpose to do a complete stall test campaign with artificial ice shapes which are fitted on the aircraft. So they look like that. This was the wing, this is the rudder, the fin, sorry, and here is the horizontal tail. Those shapes are calculated by the design office, taking into account very strict rules edicted by the regulation, and generally they correspond to the worst case of ice accretion, which corresponds generally to holding patterns or takeoff, or during takeoff, but generally holding patterns. So the shape and the thickness of the ice shapes is defined by the case, so takeoff or holding patterns, and by some complex formulas which I absolutely do not know in the regulation. But we are confident in the people which are calculating the shapes. Okay, the last thing we have, it is the flight test engineer data station. At the back of the aircraft, the flight test engineer is seated in front of screens, and during a stall test, he has the ability to first conduct the test and then to monitor what is happening, what is the aircraft behavior, the pilot behavior also. Big brother is there. And just to call out the necessary recovery call-outs or G-brake, to announce the G-brake. But this will be detailed later on by Terry. So on that screen, in fact, you are able to look at traces, which are for the given or the pertinent parameters. You have a kind of a PFD there, and you have, which is really interesting, particularly when I explained at the beginning of the presentation, that for some configurations the CL at the CL alpha curve is so flat that you are not able to detect the G-brake. So it's good to draw the CL alpha curve in real time. And so you can switch from the vertical load factor to the CL alpha curve in and out, just to see and if you have reached the CL max. And of course the stick position also. So just let me the test. So I think we have finished with the engineering preparation. So I give the hand to Van, who will talk about the pilot preparation.
Thank you. Stephane, I was born in the southern states, and so my English isn't very good either. This is actually better, I think. So one of the things we need to learn as pilots is what is the expected behavior, as Stephane pointed out, and what is expected in terms of recovery. So before we go on a stall campaign, we spend a tremendous amount of time studying the techniques for recovery. Spend a lot of time in the simulators going through timing, the call outs, and all of those things. And it's years of preparation, really. But the briefing I'm going to give you is the same brief that I would give any new test pilot who's new to big airplanes or who may be coming from the line to see a stall for the first time in his life. So these are basic preparations. And then my colleague Terry will get into more details of the stall preparation. So the first myth to dispel is that all aircraft will stall. Boeing, Airbus, they all will stall. Normal mode, secondary mode, direct law, they can be stalled. But we make them very difficult to stall. We go to a lot of trouble to prevent this from happening. Some of the things we do are to provide an amber band on the airspeed that gives the pilot visual warning that he's approaching an area that he shouldn't be in. If you're using the auto throttle and you approach the amber band, the auto throttle system will automatically wake up, advance the thrust, and keep the airspeed above the amber band. If for some reason you as the pilot turn off the auto throttle and continue to slow down, the airplane will announce a caution beeper and an airspeed load message or something along those lines. Paul mentioned the pop-up PLI indication. You'll also get that as a visual warning that you're approaching an angle of attack that you shouldn't be at. We inhibit the pitch trim in almost all of these airplanes so that you cannot continue to trim. The forces on the column or stick will build. We then have a stick shaker that will go off on both sides of the airplane. And if for some reason you have the autopilot engaged, the autopilot will remain engaged, pitch the airplane over, and protect at the stick shaker alpha plus or minus about a half a degree. The 787 and all Airbus products protect at around CLmax in the normal mode. These airplanes are extremely difficult to stall in normal mode, but it can be done. So what are the expected 1G stall characteristics for a large airplane? Typically, we see buffet begin a few knots prior to stick shaker, a slight amount of buffet, similar to ice on the horizontal tail. As you continue to slow, and as you approach CLmax, the buffet level goes up dramatically. And this isn't anything like what you've seen in small airplanes. The buffet level is about like this. It's a major hammering in the airplane. You can't see the instruments. Very difficult to read the instruments in the back of the airplane, but it's a big hammering effect, like going down railroad tracks. In fact, it's not uncommon to see a vertical component of plus or minus 1G, and even a lateral component of plus or minus a half a G. This data was taken from a flight test campaign. You can see the vertical G is about that, horizontal G is somewhat less. That's the top scaling, that's the vertical component here, and this is the sideways component. Sometimes you get a mix, and I think John Cashman called this his washing machine. So my expectations for a new plane are to see what I'd call deterrent buffet in a flaps up or clean configuration. And then with flaps down, I would expect to see the airplane get to the aft stick. So there's some differences between low altitude and high altitude. And I'll just touch upon those, and then Terry will follow up a little bit more. So another myth, the technique used to recover a big airplane is nearly identical to that used in a small airplane. First and foremost, you've got to lower the nose. You've got to push the nose over with the elevator. Altitude is of secondary importance to angle of attack. You must be willing to trade altitude if you want to recover. You have to be very careful with engine thrust. There are times when it might help, but there are other times when it might hinder. As Stefan mentioned, there's a big pitch-up effect. There are times when you might want that, and other times you might want to remain in idle until you're fully recovered. I caution our pilots to be very, very careful with thrust application. The other thing you have to keep in mind is that the buffet level may increase during the recovery. This is to be expected. I've seen some pilots stop doing what they're doing because the buffet level went up. That's probably the wrong thing to do. The buffet level might increase during recovery, continue. The restoration of normal pitch and roll attitudes, again, is of secondary importance. Get the nose down, worry about the roll later. Turning stalls. Some differences between straight ahead and turning stalls in big airplanes. We find that a sequential approach to recovery works best. First, you want to lower the nose with the elevator. You may need pitch trim in some cases. As the airplane begins to build in airspeed, smoothly roll back to the horizon. So, dual axis recovery. This is the simultaneous use of pitch and roll. When you get into that situation where the wing is really low, there's a very strong tendency to want to do it all at once. Strongly, strongly disadvised. If you're not careful, you can get the fuselage going one direction and the tail going the other. There's a lot of torque stress on the tail. You can do damage, you can set off your comms alerting system, and the next thing you know, you'll be headed home for a either repair or an inspection. So we recommend one step at a time. Pitch over, speed increasing, roll out. Very, very carefully done. Rudder on conventional airplanes normally isn't needed for recovery. We do use it a little bit for setup. As you approach the stall, you might need just a little bit of the top rudder to get the wings level. You want to go into the stall with the wings level for straight ahead stalls. But for recovery, I don't recommend it. Again, if you don't use rudder properly, you can over torque the tail and end the day. Recovery techniques for high altitude stalls. There's three things I like to brief our pilots in the sim and prior to flying. First is stall identification. Is it low speed or high speed buffet? Sometimes it's difficult to tell. If you don't intend to stall, cross-check the instruments. Test pilots, all pilots for that matter, should be very familiar with what normal is. What approximately normal should look like. What's the normal pitch attitude? What's the normal thrust level? Approximately. Those numbers can keep you out of great trouble. 12 degrees of pitch is not normal. 2 degrees, 3 degrees, that's normal. Thrust to idle is not normal. Mid-thrust. Know what those numbers look like. Know how to break the stall. The key is the elevator or the step. You have to break the stall. And the third thing is you have to be very, very patient at high altitude. It's going to take a long time to recover. Terry will get into this a little more in just a moment. Thrust is ineffective. You must trade altitude for airspeed. I can't overstate that. You must be willing to give up thousands of feet to recover the airplane from stall. It takes time. Don't be in a rush to pull on the elevator. We train our crews to follow the pitch limit indicator. Put the nose on the PLI and follow it back to the horizon. But be very careful with elevator because you'll just delay recovery and perhaps enter into a secondary stall. So that is the end of the pilot preparations, simulator studies, and then the airborne trials. So I'd like to turn it over to Terry, who's going to talk about more details that come with test conduct.
Thank you, Van. Thanks to my colleagues for setting the stage for the final aspect of stall testing, and that's how do you organize it on test day, and then how do you go out and actually begin your test campaign for a given airplane. First thing that we want to do is, as Steph mentioned, is you want to start with an airplane that's very precisely calibrated. You want to make sure that all of your air data instruments are the ones that will give you the best readings and the most accuracy for the test that you're going to conduct. From the cockpit standpoint, the pilots need to have an angle of attack and a side slip angle gauge, and probably NZ available to them directly in view, not where they have to look across the cockpit or down at the cockpit, but something right up in front so that they can easily understand what angle of attack, angle of side slip, and G are doing. If you're going to be doing stalls close to the forward CG limit, you want to have an AOA probe fitted to the top surface of the horizontal tail. And lastly, you want to sweep the airplane for any foreign objects. It is possible that you can unload, or the airplane will unload itself to 0G or maybe slightly below, and anything that's not used by the flight crew can float up into the air. Something as simple as a water bottle can hit you and be very unpleasant. So you have to prepare the airplane just like you would if you were doing real negative G testing with a large transport airplane. Pre-flight briefing. In addition to many of the other details of what we'd already studied, what we've known about the airplane from the studies and analysis, what we've learned about the airplane from the simulator and working together as a team in the simulator, now it's time for the pre-flight briefing. What we want to do is do a review of the predicted characteristics and all the limits that we've learned from those previous hours of work. We want to know what the maximum angle of attack we can expect to use. We want to know what the limits are for angle of attack. Same thing for side slip angle. We want to know what our maximum roll can be during the approach to a stall. If roll gets out of a certain limit, then we knock it off and we start over again. You want to know what the maximum side slip angle can be, and you want to respect that, and also know what the yaw damper will do to you if you're recovering and you have a high side slip angle, because the yaw damper can try to reduce side slip angle, and while doing that, it will give you a lot of roll that you might not want. We want to look at roles. We want to look at communications among the crew, and we want to look at voice call-outs. I'm going to talk a little bit more about the specific roles, but what we do is we assign duties to each particular person on the crew. We normally fly with a minimum crew. We have 2 pilots. We have a test flight engineer who sits in the cockpit, monitors the aircraft and its systems, and then we have the flight test engineer who's in the back. All 4 of us are on hot mic intercom, and all 4 of us can hear the radio. We also have a telemetry chief on the ground. Telemetry chief doesn't have hot mic, but he is on at any time. If we want to talk to him, he can transmit up to us, and he's also listening on the ATC frequency. So if you just think about this particular slide and what I've talked about up to this point, you see that everything that we've done up to this point is building up a safety net around us. We want to know we're going to stay within a certain box. We want to well define that box, and then we want to put a little bit of safeguard around us. So if we miss something, we miss a radio call or something like that, we could be reminded by any other crew member or the telemetry chief on the ground. Same thing for any parameter. And it's important that the telemetry chief be monitoring all of our parameters, because we could lose something on the airplane that he might have on the ground. So we work together as a team to stay within a box and provide some margin on the outside of that box. Weather conditions. Obviously you want to have good weather. But a lot of times you can't choose the day that you're going to fly. You're going to have to look and say, okay, the weather's acceptable today. You get up in the air and you say, okay, what have I got to work with? The first thing that you need is a discernible horizon. And we all know that. We all realize that. But the main thing is the human pilots are, once they know where that discernible horizon is, they use peripheral vision to have a sense for attitude. So if you're looking into the cockpit, looking at angle of attack, or looking at side slip, looking at pitch attitude, you know through your peripheral vision what your approximate attitude is in the outside world. So it's important that you have a discernible horizon. It's not necessary that you have no clouds, particularly no clouds above you, because if you have a high scattered layer of cirrus, that actually helps you, because you'll start the increase in angle of attack by monitoring your pitch attitude in the outside world. And if you use a head-up display, pitch attitude, or any other mark on the windscreen, doesn't have to be anything other than a bug stain, you're going to be able to immediately see changes in pitch attitude and side slip angle that you might not have expected. So you do have to have something around you, some other cloud in the background, so that you can reference that. The altitude block that we normally use is the block 8,000 feet to 14,000 feet. And the reason that we choose that particular block is because if we can conduct all of our initial stall testing in that block, we can avoid any Mach effect. So we'll do all of our testing in that particular block, and then if we want to determine Mach effects, now we know exactly what the stall characteristics of the airplane are, and we can do some stalls lower than that block and some stalls higher than that block. If you looked at the slides that Steph had earlier about the Mach effects on CL alpha, you'll notice that his Mach number was only up around 0.4 or maybe slightly higher. So that's really all we're looking at, and you can achieve that around flight level 200. In addition, most transport airplanes have a limitation where you can't use any of your high lift devices above flight level 200. So that's the reason that we do the Mach sensitivity tests a little bit below this block and a little bit above that block. It's obvious that we want to be over flat terrain. How much terrain clearance do you want to have? You probably want to have about twice the terrain clearance as your altitude block. So let's say if you have an altitude block of 6,000 feet, you need to have terrain clearance below your block of about 6,000 feet also. So you can tolerate altitudes below you, terrain elevations below you in the 1,000 to 2,000 foot range. And typically, if you're in the desert southwest of the United States and in around Toulouse, we're about 500 feet, so that fits very, very well. You can expect to lose in the stalls at this altitude range about 1,500 to 2,500 feet. So let's say on average you lose 2,000 feet during a stall. If you start at the top of the block and the characteristics of the airplane are well known, you can do one stall and recover. Start the second stall at flight level 120 and recover. So do the third stall at flight level 100 and recover, and now you're right at the bottom of your block. If you're doing the first stall tests on a new airplane, you probably want to do them all at the top of the block so you have the maximum altitude in case you encounter a surprise. Cloud clearance. That's also just kind of a judgment call. In general, you probably want to have about 5,000 feet between the bottom of your block and the top of the clouds. So if you have a cloud layer underneath where the tops are in the 3,000 to 4,000 foot range, that's probably acceptable. And you want to make sure that the zone that you're working in allows you to do repositioning turns as well, because what you don't want to do is waste a lot of time searching for a clear area. You want to make sure that you've got a clear enough area where you can do a series of stalls, and then while you're climbing back up again, reposition. So the clouds in the area and laterally are also a consideration. Then you have to look at sun angle. You can never really plan for the time of the year when you're going to do stalls. In the winter time, you have fewer hours of daylight, and the sun is generally at a lower angle. The ideal time would be the middle of the summer. You go out in the middle of the day, and the light's all on top of you, and you don't have a problem. What you want to be able to do is shield the pilot's eyes as much as possible, and you also want to avoid deep shadows in the cockpit. So it's a consideration if for example, you have a low sun angle and everybody's wearing sunglasses, you can get yourself into a situation where you have a very deep shadow in the cockpit and you might miss something on some of the flight instruments. So that's a consideration as well. How do we set up the flight control laws? That's something that I think you'll find very interesting. We have on the Airbus airplanes what we call a direct law, which is proportional, but it does have some limits. It is non-linear when you get close to full back stick, and there's a very good reason for that. With our design, when you take off in direct law and it transitions to normal law, but when you come in to flare and land, the opposite effect occurs. You transition from normal law into direct law over a period of seconds. And the conventional direct law allows you to have a little bit more stick authority close to full back stick in order to accommodate flare and landing and ground effect. So that's not necessarily a desirable characteristic. So we need to modify that a little bit, and I'll explain. Also, the deflections in direct law are reduced compared to normal law, and the reason for that is direct law is designed as a get-home mode if you've had a certain number of systems failures, and it allows you to use full back stick if necessary, but it will always keep you within the load limits of the airplane. So how do we set the airplane up if we want to do stalls? Because obviously With simple direct law, there are some limitations. Well, what we do is we install what we call a stall law, which is fully proportional and doesn't have that sensitivity close to full back stick. Well, another question that a lot of people have is, well, how do you put yourself into these specific control laws? Do you turn off computers? Do you disable an ADR or something like that? And actually, no, we don't. And what we do is something that Paul has alluded to, is there's so much information and so much connectivity on the data buses in the airplane. What we do is ask our own instrumentation to communicate with the data bus on the airplane. And in fact, what we do is we inject this law. Without turning anything off, we inject this state, so to speak, so that the airplane transitions into stall law. And what we do is we test this on the ground, because what Steph will do is he will install that particular module in the instrumentation, start the airplane, and before we taxi, he'll put that law in, and we'll do flight control checks and make sure that the control sweeps that we're recording in the airplane are what we expect for that particular stall law. And then for takeoff, what we'll do is he'll take that module out, we'll recheck our flight controls, make sure we're in normal law for flight control checks, and we'll take off and then install the module in flight. Stall law, the deflections give us that same protection in terms of staying within load limits, but what it does is, because it doesn't have that sensitivity close to full back stick, it allows us to very easily, with proportional control, see any anomalies that are happening with the airplane. And another thing that we have installed with stall law is that if the pilot is not perfectly pulling full back stick because of the geometry of your hand, it will inhibit any spoiler deflections with very, very small stick deflections. If you get any spoiler deflection, the purpose of the stall is really irrelevant, so you have to knock it off and start again. So if we can do these stalls, if the pilot makes a small error, it will not trigger any spoiler deflection. We do have a pre-stall checklist. This is outlined in our flight test guide. We start by setting pitch trim. We set that at 1.23 VS1G. We set pitch trim in idle thrust. So what the test pilot does is he goes to the top of the altitude block, level 140, goes to idle thrust. The stall law should already have been installed, and you're very close to the speed 1.23 VS1G. So you use the manual trim and you try to get that absolutely perfect, so it's holding that speed for VS1G. And you might lose, 500 to 800 feet while you're setting the trim to get it just perfect. Then you want to climb back to the top of your altitude block. Well, now when you apply thrust, you find that you're flying with forward stick and you're climbing. So it's kind of an unusual feeling, but the object is to set the trim and then leave the trim set for the whole stall series so that you don't have to repeat that exercise of setting the trim. Flight controls, as I mentioned, go into stall law. The ignition will be on. If it's the first stalls with a brand new aircraft, which has a brand new engine, you want to have the ignition on just in case the engine can't tolerate that angle of attack that you're going to get. After that, once you're confident of the engine's at that angle of attack, then you probably want to turn it off, because the ignition modules are sensitive and you don't want to burn out something that you really might need later on. Fuel imbalance is also a consideration. Most of the fuel carried in transport airplanes is carried in the wing. You want to make sure that you monitor that so that for whatever reason a lateral imbalance has not been generated. Configuration, you might be testing, depending on the objective of that particular day, you might be testing in configuration full, so you want to make sure you have the right configuration. Altitude, as we've already discussed. Thrust is at idle for the stall. And rudder. Rudder is interesting because we've all talked about you don't want to use any rudder for stall testing, but it can be your friend when you're trimming the airplane. What you want to do is have the airplane absolutely wings level with no pilot input. And you can do that by using a little bit of rudder trim, which introduces a really small amount of beta, and that small amount of beta will accommodate a small lateral offset for whatever reason. So you retrim at 0 bank angle change, and now you're just about ready to start. The last thing you want to do is review your predicted AOA limits. Not only do you want to review where you expect the airplane to stall, You want to review a pre-briefed angle of attack so that if the airplane continues and it doesn't appear to be stalled, and you get past what you think the target is, when you get to that margin above your prediction, you say, okay, recover. It's not a break call, it's a recover call. So, roles and responsibilities. The flight test engineer is really the boss. He acts as the test director. Even though he gives very little respect to pilots, we give a lot of respect to him. He does all of the pre-flight planning for us, works with the design office, he collates all of the information, all of the things that we've done prior to this, and he also provides the stall boundary definition. He's responsible for configuring both the airplane and the flight test instrumentation. And back in his panel, as you saw during the animations, he closely monitors AOA and side slip angle and November's NZ. And he calls brake. It's his job to, he's the one that uses that word. He's the one and the only one that uses that word. He calls brake when lift coefficient and NZ begin to drop. And it's important to remember that he uses the word brake because it discriminates from the word recover, which anybody else can use. If they see any parameter going outside of limits, they say recover. And it doesn't matter what your angle of attack is, the pilots will recover. The test pilots, as we mentioned, we want to make sure the airplane is in proper trim. We try to decelerate very, very smoothly without any spoiler extension. And then we monitor carefully that airplane. As I mentioned, you're looking outside and making sure that if you see any unpredicted motions, if you hear the brake call or anybody else says recover, you recover the airplane and lower the angle of attack. So now we've got a brand new airplane, brand new set of engines. We've run our checklist. How do we approach testing a brand new airplane? Normally those tests are begun at mid-CG, and the reason that we do that is because it's a very nice compromise between stability and maneuverability. Then it's the job of the pilot to decelerate at a rate of 1 knot per second to the target AOA and recover as appropriate. So how do we generate 1 knot per second rate of deceleration? On the PFD, on the airspeed scale, we have a speed trend arrow. Both the Boeing aircraft and the Airbus airplanes have this. And what we do is we want to see a speed trend arrow of about 10 knots in deceleration. You don't really focus on it, but you just put it in your cross deck and say, okay, that's what I've got. And then you begin a very, very smooth backstick motion. What we want to do is examine recovery characteristics from each target AOA in a build-up fashion. So for example, if we think that the stall will occur at 20 degrees, we'll start somewhere around 12 degrees. Decelerate to 12 degrees and recover. Everything is okay, we have positive elevator control. We'll go to the next higher angle of attack, maybe 14 degrees. And we work ourselves up to make sure we just don't go right to the end point and recover. We go slowly to the end point and make sure that we have the elevator control necessary for the recovery. If we find that we're reaching full back stick and we haven't gotten to the target AOA yet, as confirmed by the flight test engineer, what we might do is retrim the airplane. Instead of 1.23 VS1G, we're allowed to go to 1.13 VS1G, and that may give us the additional nose-up trim and elevator that we need to get to the stall. Sometimes it's necessary, even though we've used a little bit of rudder trim for wings level, sometimes because of asymmetric shedding of vortices from one side to the other, we may get just a little bit of roll-off as we're decelerating and going to higher and higher alpha. What we can do is use a very small amount of rudder, and I want to emphasize that. It's just like you've leaned the weight of your foot on the rudder, and that's usually just enough to counter a very small roll-off. But it also puts responsibility on the non-flying pilot to monitor beta, because beta can seem innocuous at maybe a half a degree, and if he gets concentrating on something else and looks over at beta, it might be 3 degrees. And it's surreptitious. Sometimes you cannot feel it as you're concentrating on decelerating. And that's why it's important at all times to brief specific parameters and monitor the parameters that you've been briefed to do. Okay, as Steph mentioned, there's going to be some pitch up. We expect it, but the technique is if you see pitch up coming, don't ease the stick forward to counter it. Just stop your F stick input or maybe slow it down just a little bit. You don't want to reverse what you've already started. You want to just continue to smoothly come back on the stick, but maybe with a slightly lower rate. And finally, what you really want to avoid is rushing the approach to the stall, the rush with your increase in angle of attack, because you could get to a high pitch attitude in a rapidly decreasing airspeed situation, which is undesirable. We say that this is 1G stall testing, and we would like to think that it is perfectly 1G, but in fact it's not, because if you, for example, have a flight path marker, and you put the flight path marker on the horizon and hold it there, and you try to hold it there, because I'm going to stay really, really level, what happens is you end up with an increasing rate of AOA as you get to the stall. And you want to avoid that rate. You want to have a nice, constant rate of angle of attack increase. So what you'll end up doing is lowering the descent rate of the airplane will increase slightly. So it won't be exactly 1G flight, but you may only lose 150 or 200 feet before you get to the stall. It's that small. But what you want to do is concentrate on that smooth AOA rate rather than trying to hold the airplane in level flight. Buffeting can be very substantial in the cockpit. So, stall recovery technique. At the brake call, smoothly reduce AOA. And the way I describe it, similar to the way Van was describing it, is you fly into the stall and you fly back out of the stall. And there's a very important reason for that. If you rapidly reduce angle of attack, depending on the size of the airplane that you're flying and your flap configuration, you can put the horizontal tail into the stalled wake of the wing before it's actually stopped making those gigantic vortices and really overload the tail. So fly the airplane into the stall and fly the airplane back out of the stall. If a wing drops at the stall or during recovery, avoid using rudder. Recover to wings level with ailerons once AOA has decreased. During the stall recovery, you can expect a pitch attitude anomaly around -5, -10 degrees and an altitude loss in the low altitude block of around 1,500 to 2,500 feet. Carefully monitor your AOA during recovery. It's going to be a funny feeling because you'll be above your trim airspeed, so the stick is going to be forward, and then you're going to increase thrust and the nose is going to pitch up and your stick might be a little further forward and you're climbing. So it's going to be a very unusual feeling airplane, and that's why you have to carefully monitor AOA at all times. So we've done the basic stalls on the airplane at mid CG. Now we want to go to forward CG, and there are a few traps to watch out for. I'll brief those. You want to make sure that that probe is installed on the horizontal tail for horizontal tail AOA, and you begin the testing in the clean configuration. You have to very carefully measure the horizontal tail AOA, particularly as the flap deflection begins to increase as you get more and more experienced with the stalls. The highest risk case is when the airplane is fully configured. And the reason is that you've got a lot of flow deflection coming up over the leading edge of the wing, over the wing, and down across the flaps. And what that represents to the leading edge of the horizontal tail is a fairly high angle of attack. And there is a risk that the horizontal tail will stall during the recovery. So think about how this actually happens. You're increasing angle of attack slowly, and as you get to the stall, the flow separates over the flaps. So it's no longer at a very high angle, and then you recover, you reattach the flow, and the flow goes to a really high angle. If you stall the horizontal tail, the airplane will pitch down and could lead to catastrophic results. So there is a risk of horizontal tail stall during recovery. So what we do is we do a series of pushovers, and we start these pushovers a lot like we do first stalls on a brand new airplane. We start at increasing angles of attack, and we also use increasing deflections of the stick during recovery. So we might start at, say, 12 degrees angle of attack and recover with, say, 1/4 forward stick, and then we might go 1/2 forward stick. And we increase those deflections and angles of attack until we're at the stall, and we progressively increase the stick deflection to 2/3 of full forward stick. What we want to achieve is a 2-degree margin to the horizontal tail stall, and the reason for that is because shortly after that we're going to put those nice ice shapes on the airplane, and we want to have a little bit of extra margin in case something changes at the horizontal tail aerodynamically. What about stalls at AFCG? The high risk factors in FCG are the possibility of a lateral departure, a side slip type of departure, or an increase in the amount of pitch up that you have. The worst case is the amount of nose-down authority that you have remaining with full forward stick to counter any nose-up pitching moment that might occur if the pilot were to apply toga thrust on the airplane. The build-up to the stall is basically the same as for first stalls, but the recovery must be started immediately if any limits are exceeded, because angle of attack can increase on its own very rapidly. With a strong pitch up, we will conservatively set the threshold for stall warning at a slightly lower value of angle of attack, but because we know that the angle of attack rate can be increasing fast enough, we want to give the pilot a little bit more advance warning so we can begin to recover. Question may be in many of your minds, if you have a fly-by-wire airplane that's supposed to be stall protected, how do you certify it? How do you get it by the authorities? You know, how do you get through the certification requirements for stalls? It's a very good question. We start initially in normal law with forward CG, and normally we do this because there is the possibility, because of the atmosphere and the effects of wind shear and some other things, it is possible for angle attack to increase above the stall, even in normal law, even if the airplane is angle attack protected. Well, how do we actually stall the airplane in normal law? It's kind of an interesting thing. What we do is we go back into that ATIS module, we create one which puts the angle of attack limit higher than it normally would be. So let's say if the limit were placed at 15 degrees in your protection limit, giving yourself a margin to the stall, we're going to add 10 degrees in the clean configuration so that we can be in normal law and stall the airplane. In the fully configured case, we add 7 degrees to that. So we also do additional stalls in degraded control laws, for example, alternate law and some others. And one thing that we have to keep in mind is when we're in augmented control laws, anytime we have a NZ pitch rate, angle of attack feedback in the flight control laws, the airplane is going to, by design, attempt to maintain 1G flight, and it will do automatically whatever it wants to do to maintain that. So you may find an additional amount of forward stick necessary for recovery to avoid more nose-up elevator than you want at the G rate. Stalls at high Mach number. We talked about that just a little bit earlier. In several of the graphs, you can see that as you get to higher and higher and higher Mach number, you have less and less CL available to you. In fact, it's to the point where it's a noticeable decrease in AOA margin. And it's also to the point where if you think that your airplane is, airplane that stalls at, say, 19 degrees angle of attack at 14,000 feet, it might only stall at 8 or 9 degrees angle of attack at high altitude and high Mach number. Also, one of the things that was shown in an earlier slide, and I'm going to talk about a little bit more, is that as Mach decreases, AOA margin increases, and the reverse is true. As Mach increases, AOA margin decreases, and I'll show you how that works. Determining the point of the stall at high Mach is difficult. The amount of vibration, as you saw in that video, the amount of vibration in the cockpit and at the flight engineer station is such that the engineer can no longer really clearly see the G brake on the G trace or the CL alpha brake on the CL alpha trace. There's just too much noise in the signal because of the buffet. What may be the first indication to the crew that your stall is a very rapid increase in vertical velocity at the stall. Again, as Van mentioned, he talked about it very clearly at high Mach number. You have to be smooth, but you have to be positive, and you have to be patient. Once again, it doesn't take a very strong nose-down pitch attitude. If you happen to look at the PFD in that video, you would find that they were between 5 and 10 degrees nose-down pitch attitude to recover. So that's about what you would expect. And you'll also notice that as you accelerate in the recovery, that pitch up tendency that you had will actually translate to a little bit of pitch down, which will help you. If you do use thrust, the pitch down will actually be countered a little bit with the thrust pushing the nose up. So it's a fairly benign recovery, other than the fact that you have to be patient and let the airplane accelerate and expect that you're going to lose 5,000 to 7,000 feet from a stall at high Mach number. So let's take a look. Considerations for recovery. As I mentioned, as acceleration increases, your AOA margin decreases, and you have to kind of wrap your head around that, and I'm going to show you a graphic here shortly. Forward stick has to be maintained, And if you try to recover a little bit early, you may get back into deterrent buffet and trigger the stall warning. So here's where you start. If you look at this chart, you're going to be here at about 8.2 Mach. That's a normal cruise point for a transport category airplane. And if you look at your angle of attack, you're going to be just about 2.5 degrees, maybe touching 3 degrees. So let's say that you do a deceleration, a normal 1 knot per second deceleration to deterrent buffet, which is defined by this line here. And what we want to look at is what our AOA margin is. So you begin your recovery there, and here's what your AOA margin looks like. All right, you're up here close to the buffet line, right at the buffet line. You recover. You go back down to an angle of attack around 3.5 degrees, and then you maybe use a little bit too much backstick. Mach number is increasing, but look at your angle of attack margin, which is decreasing. And that's something that you have to pay close attention to and keep in your mind. As you recover and your Mach number increases, you think, hey, I'm safe, I got more speed, I got more Mach. In fact, your margin is decreasing, so you have to be careful. Okay, I'm going to turn it back over to Paul for our conclusion. Thank you very much.
Okay, now that we've told you everything about preparing for and conducting stalls, we just wanted to touch real briefly on some questions more than answers, but some questions about where we might be going into the future. So we've talked a lot about systems augmentation. We've talked a lot about the regulations. In the last decade or so, or maybe a decade and a half, there's been quite a lot of focus on stalls. Will that continue? My personal opinion is probably. I mean, this is a highly high-risk environment for aircraft, so as long as the aircraft can still stall, I'm sure we'll still be stalling them for regulations. The industry, at least the large transport industry, as has been mentioned, has been moving down this path towards preventing stalls, really. We've gone to, on the Boeing side with the 787 and with all of the Airbus airplanes, gone to an angle of attack limiting philosophy. The sub-bullet there is trying to get at it. It's really hard to imagine a requirement for an airplane to be flying around in a stalled flight condition. So there's really no reason not to prevent the stall environment. What about adding augmentation to degraded modes? Right now, on all of our aircraft, we do a great job of augmenting and protecting and limiting in our normal flight control laws. But once those have degraded into secondary, alternate, direct, whatever the nomenclature is, a lot of that protection goes away right now. Could we develop a way to provide some kind of angle of attack limiting in those degraded modes as well? We don't do that now, but perhaps that's a good idea moving forward. It'd be very problematic to do, but something we should probably look into. And in fact, if we do continue down this road and stall or angle of attack limiting becomes the standard for these large transport airplanes, and once we've established a track record that it's reliable enough that the protection is always going to be there, will we even continue to demonstrate stalls? It's kind of hard to imagine not doing that for a flight test campaign, but it's at least a question going forward. And we do a lot of work on these airplanes these days to move the protections out of the way to conduct these stalls. It's possible going forward that with the limiting becoming more and more strong, without doing some kind of system intervention, it may not be possible to stall these airplanes. We talked a little bit about how we're having to move some of our protections out of the way just to conduct stalls now. And, are we really skilled enough as engineers and pilots to envision everything that could possibly happen to an airplane? If we don't do stall testing on some future aircraft, we would limit our ability to predict what the high angle of attack regime would be like and what it would feel like. And do we know for a fact that we could prevent every stall all the time? Probably still a good idea to do these just to get that information. So there's some thoughts on the future, and of course we're going to summarize as we draw this to a close. Some of the things we've done, we've shown how our two large flight test organizations discuss, plan for, predict, prep, brief, and actually conduct stall testing. We've also included insights from both the engineering side of the community as well as the pilot's view on what goes into preparation and conducting stall testing. We've shown some videos, some of which, as Van was mentioning, have never seen the light of day outside of the companies before, both from the outside view of the airplane as well as a few from inside the airplane of what some of this testing actually looks like. And I closed just a minute ago with at least some thoughts or questions about stall testing going forward into the future. We learned quite a bit, our little team of 4, from our cooperative effort. As we mentioned with a little bit of humor on the first slide, the title slide, this is, as far as we know, this is the first time a joint Boeing Airbus endeavor such as this has been undertaken. We learned a lot from each other. Perhaps surprisingly, perhaps not. Much of what we do in our 2 companies to conduct this type of testing is very similar. There's a lot of differences, especially in sales campaigns, but a lot of what we do is similar. And where there is differences, some of that's intriguing. Again, we learned a lot from one another about, well, why does your company do things this way? Why does your company do that way? So it was very educational for us in a non-competitive sense. I think the primary conclusion we came to is that the sales guys aside, when it comes to conducting flight tests, and this particular topic is stalls, but any kind of flight test really, when it comes to safety, there's really no competition. And our high-level management of the flight test organizations of both of our companies are very much behind this thought, that where safety is involved, there's no reason for us not to communicate, not to cooperate, not to collaborate. And this presentation was one of the first endeavors as a result of that meeting of the minds, if you will, of our high-level management. And with that, we are at a close. I'd like to thank you for your time and attention tonight. And I think we'll move over to the panel position here to answer any questions you might have, and Andy will moderate. So thank you very much for your time.